Ancient civilizations built machines that should not have existed for another 1,000 years. We are about to explore 25 ancient inventions that were centuries ahead of their time, revealing a hidden history of technological genius. By the end, your entire view of human progress will be reshaped as you discover devices that predicted celestial events and materials that defied decay. How did a 2,000-year-old computer accurately track the stars, and why was a Roman cup able to change color with a trick of the light? What does it truly mean to be ahead of your time? We often think of history as a straight line of progress, but this view is a trap of our own making. The truth is far more interesting. To understand the marvels we are about to uncover, we must first abandon the idea that ancient times were simple or dark. Picture instead the vibrant intellectual centers of the past. In Alexandria, a library aimed to collect all the world's knowledge, its scholars debating geometry and the nature of the stars. During the Islamic Golden Age, observatories dotted the skies and houses of wisdom preserved and expanded upon ancient texts. In imperial China, meticulous astronomers tracked celestial movements for generations. These were not societies groping in the dark. They were hubs of intense inquiry, powered by a sophisticated grasp of mathematics and a keen observation of the natural world. Their groundbreaking inventions did not appear from nowhere. They were the direct result of this cultivated environment where skilled craftsmanship met deep, systematic research. This foundational genius is the very bedrock upon which our story of impossible technology is built. That corroded lump of bronze, hauled from the seafloor after 2,000 years, held a secret that would force us to rewrite history. When archaeologists first brushed away the incrustations, they found not a statue or a weapon, but the intricate traces of precisely cut gears, all fused together by time and seawater. This was the Antikythera Mechanism. To call it a simple clockwork would be like calling a modern supercomputer a fancy abacus. It was a portable universe engineered in bronze. Its dozens of interlocking gears worked in concert to mirror the erratic dance of the planets, forecast lunar and solar eclipses, and track the cycles of the Panhellenic Games, a 4-year calendar of athletic and cultural festivals that unified the Greek world. The genius of its design lies in its differential gearing, a complex arrangement that allows two wheels to rotate at different speeds while sharing a single axis. This precise engineering, which would not reappear in the historical record until the 19th century, enabled the mechanism to account for the subtle variations in the Moon's orbit. Think of the challenge. The creators had to translate the abstract, mathematical rhythms of the cosmos into the physical turn of a hand crank. One rotation of the input dial could set dozens of gears in motion, calculating celestial events years into the future with a quiet, mechanical certainty. This was not magic. It was applied knowledge of the highest order, a product of a civilization that had observed the heavens for centuries and possessed the engineering skill to build a machine to model them. How could such sophistication vanish from the world for over 1,000 years? The answer lies in the fragility of knowledge itself. While the Antikythera Mechanism mapped the heavens, another ancient innovation harnessed a more earthly and terrifying power. Picture a Byzantine warship, a Dromon, surrounded by enemy vessels on the open sea. With a terrifying roar, a tube mounted on its bow unleashes a torrent of liquid flame. This was Greek fire, a weapon so potent it could not be put out with water, seeming to burn the very ocean itself as it clung to ships and men. For centuries, this fearsome substance was the ultimate naval weapon, a closely guarded state secret of the Byzantine Empire that allowed their outnumbered fleets to defend their civilization against overwhelming odds. Its exact formula died with the empire, and to this day, its composition remains one of history's great unsolved puzzles. Scholars believe it likely involved crude petroleum or naphtha, mixed with other ingredients like resin or sulfur to create a sticky, persistent inferno. It was pumped through pressurized siphons, a technology that would not be matched until the flamethrowers of the 20th century. This was not merely a weapon of war, but the product of advanced alchemical research, a chemical weapon born from generations of experimentation. The secret was so valuable that only a single family, and perhaps the emperor himself, were trusted with its recipe. Its very mystery was its strength. How do you defend against a fire that water only fuels, a weapon whose nature you cannot comprehend? The power of Greek fire lay not just in its destructive capability, but in the profound psychological terror it inflicted, a blazing testament to the fact that ancient science could produce forces that felt, to those who faced them, like pure magic. While Greek fire unleashed a visible and terrifying power, a far subtler form of energy might have been at work in an ancient workshop. In the archives of the National Museum of Iraq rests a deceptively simple object, a small clay jar no larger than your hand. Inside, a copper cylinder houses an iron rod, and the whole assembly is sealed at the top with a stopper made of asphalt. Found in the ruins of Qujat Rabu near Baghdad, this artifact from the Parthian or Sassanid era, some 2,000 years ago, looks nothing like a weapon. It looks for all the world like a primitive battery. Modern experiments have proven the point. When filled with an acidic electrolyte, something as common as vinegar or grape juice, the jar produces a small but measurable electric current, around 1 to 2 volts. The chemical reaction between the acidic liquid, the copper, and the iron creates a basic galvanic cell, the very same principle that Alessandro Volta would not rediscover until the turn of the 19th century. So what was this ancient power used for? The most compelling theory points to electroplating, the process of using electricity to coat a common metal with a thin layer of a precious one. Imagine an artisan wanting to gild a silver statue. By placing the statue in a solution and connecting it to a series of these clay jar batteries, a faint current could slowly draw microscopic particles of gold from the solution, binding them to the surface in a seamless, durable layer. This would explain artifacts found with surprisingly fine and adherent gold plating that seems to defy simpler, fire-based gilding techniques. Other suggestions include its use in medical therapy, where the mild shock could have been applied to soothe muscle pain, a practice that would eerily prefigure modern transcutaneous electrical nerve stimulation. The true purpose may be lost, but the object itself is undeniable. It stands as a quiet, humming question mark in our timeline, a testament to the possibility that the spark of electricity was not a modern discovery, but an ancient secret, patiently waiting in a clay pot for centuries to be understood again. The silent endurance of the Pantheon's dome is a riddle written in stone. Nearly 2,000 years after Roman hands poured it, this vast, unreinforced ceiling still stands open to the sky, defying earthquakes, the elements, and the very passage of time. Modern concrete, the material that builds our world, often crumbles in mere decades, requiring constant repair. So what was the secret held within this ancient recipe? The answer lay dormant in the ruins, waiting for modern science to decipher it. Roman concrete was not just a mix of lime and rubble. Its genius ingredient was a specific type of volcanic ash, combined with chunks of lime and mixed with seawater. This combination triggers a remarkable chemical process. Over centuries, seawater filtering through the concrete dissolves the ash and lime, allowing new, ultra-durable minerals to crystallize within the gaps and cracks. These crystals act like a self-healing mechanism, locking the structure together ever more tightly as the years roll by. It is a material that grows stronger with age. Modern Portland cement, by contrast, is designed for rapid setting and initial strength, but it is brittle. When cracks form, water seeps in, rusting the internal steel rebar and causing the structure to fail from within. The Roman formula presents a stunning reversal of our entire engineering philosophy. Today, researchers are racing to reverse engineer this ancient technology, hoping to create new, self-healing concretes that could lead to seawalls that fortify themselves against storm surges, or bridges that require far less maintenance over their lifetimes. The lesson is profound. The Romans achieved a form of sustainable durability that our own civilization is only now beginning to grasp, a quiet mastery over materials that has outlasted empires. A material that changes its very essence depending on your point of view might sound like science fiction, yet this was the stunning reality of a Roman drinking vessel crafted in the 4th century. Known as the Lycurgus cup, this extraordinary artifact is a masterpiece of cage glass depicting the mythical king Lycurgus entangled in grapevines. In reflected light, it glows a deep, solid green. But hold it up to a light source and the entire scene undergoes a breathtaking transformation, blazing into a translucent, fiery red. This is not a trick of the light, but a triumph of ancient technology. The secret was locked inside the glass itself. Roman artisans, through a process we can only guess at, infused the molten glass with a precise mixture of gold and silver particles. And we are not talking about mere specks of dust. These particles were ground to an almost unimaginable fineness, each one measuring roughly 70 nanometers across. To grasp that scale, a single nanometer is 1/1000th of a meter. These particles were so small that their behavior was governed by the strange rules of quantum physics, not the classical mechanics of the everyday world. When light hits the cup, these nanoparticles scatter the light in a specific way. They absorb the blue and green wavelengths in transmitted light, allowing only the deep reds to pass through, creating that magical glow. This phenomenon, called dichroism, was an artistic effect achieved through what we now recognize as advanced nanotechnology. The Romans had no electron microscopes, no theory of quantum mechanics. They possessed only generations of empirical knowledge, a master craftsperson's intuition, and the patience to perfect a formula through relentless experimentation. They were manipulating matter at the atomic scale to produce a visual spectacle, a feat of engineering that would not be scientifically explained or replicated for another 1600 years. This cup stands as a quiet, shimmering challenge to our assumptions. It asks us how a civilization without our tools could achieve such granular control over the physical world, turning a king's myth into a permanent dance of light and color. A different kind of mystery lies pressed into a simple clay disc, unearthed in the ruins of a Minoan palace on Crete. The Phaistos disc is a small, fired clay tablet from the 2nd millennium before the Common Era. Its surface is not carved but stamped with 45 distinct symbols, arranged in a tight, curling spiral on both sides. There are marching men and helmeted heads, birds in flight and flowering branches, a whole library of tiny images that no one in the modern world has ever been able to read. This unique script, found nowhere else on Earth, is the core of its enigma, but the true revolution is not in the message but in the method of its delivery. Each symbol was not painstakingly etched by hand. Instead, they were stamped into the soft clay using individual, pre-formed punches, one for each pictograph. This is the earliest known use of movable type printing in human history. Think of the implications. A Minoan artisan, over 3,000 years before Johannes Gutenberg assembled his famous press, had conceived of a system where reusable symbols could be arranged and rearranged to convey different information. This points to a staggering level of organizational thinking and technological standardization. It suggests a society that saw the value in reproducing information efficiently, a need that typically arises with complex administration or widespread literacy. Yet this spark of genius appears to have been isolated, a technological flare that burned brightly on that one clay disk and then was snuffed out for millennia. Why was this system not used on other tablets? Was the disk a royal proclamation, a religious hymn, or a simple inventory list? We may never know what story its spirals tell, but its very existence forces us to reconsider the pace of innovation. It stands as a silent, stubborn relic of a lost information age, proving that the idea of the printing press is not a product of the Renaissance, but a concept that had already been formed and then forgotten in the deep Bronze Age. A small piece of polished rock crystal, no bigger than your thumb, holds a secret that reshapes our view of ancient site. Unearthed from the Assyrian palace of Nimrud, this 3,000-year-old artifact is ground into a precise oval with one flat side and one gently convex curve. This is the Nimrud Lens. When you hold it to the light, it does something remarkable. It bends light rays to a focal point, magnifying whatever lies beneath it and concentrating the sun's rays into a pinprick of intense heat. Was this a decorative piece on a royal throne or something far more profound? Some scholars argue it was a burning glass used to kindle fire with the power of the sun alone. Others see a more delicate purpose. Imagine an ancient jeweler or scribe, their eyes straining over the fine engraving on a seal or the tiny cuneiform wedges on a clay tablet. This crystal held up to the eye would have brought those minute details into sharp, clear focus, turning a blur into a legible mark. If this was its true function, then the Nimrud Lens is the world's oldest known magnifying glass, a tool of precision that predates the earliest known eyeglasses by nearly 2,000 years. Its very existence implies a sophisticated, practical grasp of optics in an age we often associate with brute force and monumental sculpture. This was not a society groping in the dark. They were manipulating light itself, using an understanding of refraction that would not become common knowledge for countless generations. How many other such lenses have crumbled to dust, leaving this single, crystalline clue to a lost world of focused vision and meticulous craft? The quiet hum of a city could be shattered in an instant by the rumble of the earth itself. In ancient China, the source of a distant earthquake was a profound mystery, often seen as a sign of celestial displeasure. It was into this world of uncertainty that the scholar Zhang Heng introduced a machine of stunning foresight. In the year 132, he presented the Han court with his Hufeng Didongye, an instrument for measuring the seasonal winds and the movements of the earth. This was no simple weather vane. It was a magnificent bronze urn adorned with 8 dragons staring intently downward. Each dragon clutched a bronze ball in its jaws, and directly below each one, a bronze toad waited with its mouth wide open. The elegance of its design was matched only by its purpose. When an earthquake struck, even hundreds of miles away, a precise internal mechanism would be triggered. A pendulum inside the vessel would swing, tripping a lever that caused just one dragon to release its ball. The loud clang of bronze hitting bronze would announce the event, and the specific toad that caught the ball would point unerringly in the direction of the quake's epicenter. The genius of this device lay in its ability to sense what human beings could not. There are accounts of the instrument activating with a clatter when the court itself felt nothing. only for a messenger to arrive days later from the indicated province, reporting a devastating tremor. The exact mechanics of its interior remain a subject of debate, lost to time, but its function is undeniable. Zhang Heng had given the empire a mechanical ear pressed to the ground, transforming an invisible, terrifying force into a clear, directional signal. This was the world's first seismoscope, a creation that combined artistic beauty with mechanical intuition to listen to the heartbeat of the planet itself. In 1961, 3 rockhounds hunting for geodes near Olancha, California, cracked open what seemed to be a promising specimen. Inside the hardened clay and pebbles, they did not find the expected crystal cavity. Instead, their saw revealed a circular cross-section of a hard, white material surrounding a central metal rod, all encased in a perfect shell of mineralized rock. It looked for all the world like a modern spark plug. The immediate, astounding implication was that this mechanical object had been entombed within a rock layer believed to be 500,000 years old. This was the birth of the Coso artifact legend, an out-of-place artifact that seemed to defy all known history. The mystery, however, unraveled under closer scrutiny. X-ray analysis later showed the object was not a simple mystery lump, but a precise assembly, complete with a hexagonal metal collar and a porcelain insulator. It was not a relic from a lost civilization, but almost certainly a champion spark plug from the 1920s, likely from a mining vehicle. The so-called geode was not a true geode at all, but a concretion, a hard mineral nodule that can form remarkably quickly around a man-made object left in the right conditions. This process, called concretion, can make a decades-old spark plug appear to be millions of years old to the untrained eye. The true lesson of the Coso artifact is not about ancient astronauts, but about the very human desire to find the extraordinary. It stands as a powerful cautionary tale, reminding us that our interpretations of the past are often filtered through our own assumptions and desires. Yet, this story also highlights a deeper truth. The genuine marvels of antiquity, like the intricate gears of the Antikythera Mechanism or the self-healing Roman concrete, do not need fictional origins to be awe-inspiring. Their reality, born from the ingenuity of our ancestors, is often more incredible than any manufactured mystery. While the Coso artifact teaches us to question our assumptions, other relics offer undeniable proof of ancient mastery. In the heart of Delhi's Quad complex, a 7-meter-tall iron pillar has stood for over 1,600 years, exposed to the full force of nature. It was forged in the 4th century during the peak of India's Gupta Empire, a period of immense scientific and artistic flourishing. Yet, unlike any modern steel structure, this ancient monument shows virtually no signs of rust. It has endured centuries of monsoons, scorching heat, and now the corrosive effects of modern urban pollution, yet its surface remains smooth and largely uncorrupted. This is not a lucky accident. It is the result of a sophisticated and deliberate metallurgical process that we are only now beginning to fully comprehend. The secret lies in the very composition of the iron itself. The ancient blacksmiths used an iron ore with an unusually high phosphorus content. During the forging process, they did not add lime, a common practice in modern steelmaking that removes phosphorus. Instead, they skillfully hammered and compressed the metal at a high temperature, a technique that encouraged the formation of a thin, protective film on the surface. This film is a compound called mesawite, a blend of iron, oxygen, and hydrogen that acts as a passive, self-repairing barrier. When morning dew or rain settles on the pillar, this layer reacts to form a protective coating that shields the raw iron beneath from further attack. It is a perfect natural shield born from the metal's own chemistry. Modern steel, by contrast, is often made with low phosphorus and relies on artificial coatings or alloys for protection, coatings that can chip, peel, and require constant maintenance. The pillar stands as a quiet, towering rebuke to the idea that durability is a modern invention. It represents a pinnacle of materials science, a technology of permanence achieved not with complex machinery, but with an intuitive, profound understanding of the elements. Within a vault at Yale University rests a book that refuses to be read. The Voynich Manuscript is a 240-page puzzle bound in vellum, its pages filled with a graceful, looping script that forms no known words in any known language. Since its rediscovery in the early 20th century, this early 15th century codex has resisted the efforts of the world's top cryptographers, linguists, and mathematicians, from code breakers who cracked enemy ciphers in 2 world wars to the most powerful artificial intelligence algorithms. The writing flows like a genuine language with its own consistent structure and patterns, yet it conceals a message that has remained perfectly opaque for 600 years. But the text is only half the mystery. Its illustrations plunge the viewer into a surreal world. There are sprawling botanical sections featuring plants that have no counterpart in nature, their roots and leaves arranged in impossible configurations. Astronomical charts show celestial diagrams with unfamiliar constellations and nebulas that resemble cellular structures. Most haunting are the pages depicting groups of nude women, some crowned, bathing in and connecting tubes of a vibrant, bubbling green liquid. Is this a lost treatise on alchemy, a guide to a forgotten spiritual practice, or an elaborate and masterful hoax designed to deceive a wealthy patron? The very persistence of its secrecy challenges a fundamental assumption that given enough time and intellect, any human creation can be understood. The Voynich Manuscript stands as a permanent testament to the opposite idea, that some doors from the past may remain forever locked, guarding secrets about the boundaries of late medieval knowledge that we can only glimpse but never fully grasp. Centuries before the Industrial Revolution, steam was already turning metal in an Alexandrian workshop. The great engineer Hero described a device he called an Aeolipile, a simple yet profound machine. It was a hollow sphere suspended between 2 pipes above a sealed kettle of boiling water. As the fire heated the kettle, steam rose through the pipes into the sphere, which had 2 bent nozzles protruding from its sides. When the pressurized steam shot out of these nozzles, the sphere itself began to spin, whirling faster and faster in a cloud of vapor and heat. This was not just a curiosity, it was a working demonstration of Newton's 3rd law of motion, that for every action there is an equal and opposite reaction, articulated over 1,500 years before Newton was even born. The Aeolipile was in every functional sense a reaction steam turbine. The conceptual leap to harnessing steam for power had been made, so why did the ancient world not fill with factories and locomotives? The answer lies not in a lack of genius but in a surplus of labor. The economy of the ancient Mediterranean was built on the backs of slaves and cheap workers. There was simply no pressing economic incentive to invest in the complex and costly development of steam engines to replace a workforce that was already abundant and inexpensive. The spark of an idea was there, brilliantly ignited, but the social and economic tinder to create a wildfire of industry was not. Hero's spinning sphere remains a haunting what-if, a clear signpost on a road to progress that antiquity saw, acknowledged, but ultimately had no reason to travel. The shimmering waves on the surface of a Damascus steel blade are more than just decoration. They are the visible signature of a metal that defied its era. Crafted from ingots of Indian wood steel, These legendary swords possessed a near-mythical sharpness and a resilience that could reportedly slice through a silk scarf falling through the air or shatter a lesser European blade upon impact. Their secret was forged not in a simple smithy, but in a meticulously controlled alchemy of fire and time. The process began with raw iron ore and carbon-rich materials like wood or leaves, sealed together inside a clay crucible and heated for days until the iron absorbed the carbon, creating a high-carbon steel ingot peppered with microscopic carbide. It was the next step, the forging and the incredibly slow cooling of the metal, that unlocked the true miracle. As the red-hot steel was painstakingly hammered and then allowed to cool over many hours, the carbides within it self-assembled into an intricate nanoscale architecture. Modern electron microscopes have revealed that within the finest Damascus blades, the metal is laced with carbon nanotubes and incredibly strong cementite nanowires. These are structures we associate with 21st century materials science, yet they were being grown inside sword steel over 1,000 years ago. These internal reinforcements gave the blade its legendary combination of a razor-sharp edge that resisted chipping and a flexible body that could absorb the shock of combat. The knowledge of how to consistently produce this nano-structured metal, a craft passed down through generations of master smiths, vanished in the 18th century. The exact combination of ore, carbon source, and thermal cycling was lost, perhaps as trade routes shifted or as the masters died without passing on their most subtle techniques. We can now analyze the result with our most advanced tools, but we still cannot perfectly replicate the process. The sword's beauty was literally written in its atomic structure, a masterpiece of ancient materials engineering that turned a simple weapon into a durable, self-reinforcing matrix, a technology of war that was quietly built from the nanowires up. Deep within the crypts of the Hathor temple at Dendera, a stone carving defies simple explanation. Etched into the wall is a surreal and captivating scene. It shows a massive, elongated bulb shaped almost like a pear, and inside it, a snake stretches the entire length of its body, its head touching the narrow end. This strange object is connected by a thick, cord-like line to a box, which is being held steady by a kneeling god, while a baboon-like figure raises a knife toward the cable. To a modern eye, the resemblance to an incandescent light bulb is startlingly uncanny. The bulb shape becomes the glass enclosure, the snake is the glowing filament, the box is the power source, and the cable is the wire. Could this be evidence that the ancient Egyptians harnessed electric light, perhaps using a version of the Baghdad Battery to illuminate their darkest tombs and temples? The theory is seductive, offering a clean, technological solution to the age-old question of how they painted and carved in pitch-black subterranean chambers. Yet mainstream archaeology presents a different, more symbolic reading. In this interpretation, the scene is not a technical diagram but a rich mythological tableau. The bulb is actually a lotus flower from which the snake, a symbol of the god Harsomptus, is being born. The entire image represents the Egyptian creation myth, the moment the world burst forth from the primordial waters, depicted again and again in the sacred space. This stark divide in interpretation is the true heart of the Dendera mystery. It forces us to confront a critical question. Are we seeing a literal blueprint for a forgotten technology, or are we projecting our own modern world onto a culture that thought in profoundly different, deeply symbolic terms? The carvings do not hold a secret of lost engineering, but a lesson in the humility of history. They remind us that our ancestors communicated complex ideas about life, divinity, and the cosmos through an artistic language we are still struggling to fully decipher. The light at Dendera may not have been electric, but it continues to shine, illuminating the vast gap between their worldview and our own. 15th century earthquakes have toppled countless modern structures across Peru, but the walls of Sacsayhuaman remain unshaken. These are not simple blocks stacked one upon the other. They are a colossal, three-dimensional stone puzzle, each piece a polygonal giant weighing dozens of tons, carved from granite so hard it defies modern tools without power machinery. The miracle is in the joints. The Incas shaped the underside of one stone to perfectly cradle the top of another, creating intricate, interlocking patterns that look almost organic. You cannot slide a piece of paper, let alone a razor blade, into the seams. This was not for aesthetic perfection. It was a profound understanding of seismic forces. When an earthquake strikes, a rigid wall of uniform blocks will crack and crumble as the ground heaves. But these interlocked stones dance, they shift, they rock, they settle, absorbing and dissipating the energy of the tremor without breaking apart. They are a wall with built-in flexibility, a system that moves with the earth rather than fighting against it. The deeper mystery is how they achieved this with nothing harder than stone, bronze, and sand. The prevailing theory suggests they pounded the stones with other harder river rocks, gradually shaping them over countless patient hours. They might have used sand as an abrasive to polish the final surfaces, creating that impossible airtight fit. This was not a rushed construction, it was an act of generational patience, a testament to a society that planned for millennia, not just for decades. Modern engineers now study these walls not as primitive ruins, but as masterclasses in anti-seismic design. They represent a lost art of listening to the land and building in harmony with its violent rhythms. A Stone Age solution that remains smarter in many ways than our own. The principles of flight are written in the bones of a bird, yet one ancient artifact seems to have decoded them in wood. Discovered in an Egyptian tomb at Saqqara, this sycamore carving from around 200 years before the Common Era looks at first glance like a simple bird figurine. But a closer look reveals a startling anomaly. Its wings are not rounded and organic like a falcon or a hawk. They are straight, sharply angled, and rigid, bearing the distinct, efficient profile of a modern monoplane. To most archaeologists, this object was a ceremonial piece, a child's toy, or a weather vane, its true purpose lost to ritual. To a handful of aviation engineers, however, it was something else entirely. They saw in its carefully carved form the precise aerodynamic principles of a glider. When a replica was placed in a wind tunnel, the results were startling. The Saqqara bird generated significant lift. It was aerodynamically sound. Researchers found that with just one small addition, a horizontal stabilizer on its tail to counteract its slightly nose-heavy design, the artifact could achieve stable, graceful flight. It was not merely bird-shaped, it was airworthy. So was this a scale model for a larger, forgotten flying machine, or simply the inspired guesswork of a brilliant artisan? Without any written context, we may never know the intent behind its creation, but its very existence poses a profound question. Did an ancient carver, through sheer observation and intuition, stumble upon the fundamental secrets of aerodynamics, achieving in miniature a feat that humanity would not master again for another 2,000 years? The Saqqara bird does not claim to be a blueprint for an ancient airplane, but it stands as a silent, winged testament to the fact that the dream of flight is far older than the Wright brothers, a dream once captured in the delicate grain of sycamore wood. Far beneath the soil of Han Dynasty China, a different kind of industry was taking root. While the Romans perfected their concrete and the Greeks modeled the cosmos, Chinese engineers were solving a problem of immense scale and depth. They needed salt, a vital commodity for preserving food and sustaining life, and the richest brine pools lay trapped deep underground, far beyond the reach of simple wells. Their solution was a drilling technology so advanced that it would not be rivaled in the West for nearly 2,000 years. Imagine a towering bamboo derrick, a scaffold of incredible resilience, rising against the sky. Below it, a team of workers would rhythmically jump on a lever, sending a heavy iron bit crashing down into the earth. This was a percussion drill, a method that pounded its way through rock, foot by laborious foot. But the true genius of the system lay in its supporting architecture. They built dual bamboo pipelines running from the borehole to a brine tank. One pipe carried natural gas, tapped from the very depths they were drilling, while the other was used to pump compressed air down into the hole. This air blast would force the pulverized rock and debris back up to the surface, clearing the way for the next descent of the bit. It was a closed-loop system of astonishing foresight. They could drill boreholes reaching depths of 4,800 feet, a staggering achievement that allowed them to access reservoirs of natural gas. They then channeled this gas through bamboo pipelines to fire giant evaporating pans, boiling the brine to produce salt on an industrial scale. This was not a mere hole in the ground, it was a complete extraction and utilization process. Every component, from the derrick to the pipelines to the method of debris removal, reveals a comprehensive understanding of deep earth engineering. This Han Dynasty technology was the direct, fully formed precursor to the rotary drills and derricks that would later tap the oil fields of Pennsylvania and Texas. A system born from the need for salt, it laid the entire foundational framework for the modern world's relentless pursuit of the energy hidden deep within our planet. The sheer scale of the Huaca del Sol is difficult to comprehend even when you stand before its weathered remains. This colossal adobe pyramid on the arid coast of Peru was not just a temple, it was a mountain made by human hands, the largest structure of its kind in the ancient Americas. Constructed by the Moche culture in the 5th century, its creation required a breathtaking logistical feat. The pyramid is composed of approximately 130 million sun-dried mud bricks. Each brick was not an anonymous component but a signed piece of work. Fingers, thumbs, and unique symbols were pressed into the clay while it was still soft, marks now believed to represent the specific work gangs, family clans, or entire communities tasked with their production. This was not a haphazard piling of earth. It was a highly organized, systematic enterprise, a prehistoric version of a modern construction project where every batch of material is tracked with a barcode. Imagine the coordination required to manage this supply chain. Different communities across the Moche realm would have been responsible for manufacturing their assigned quota of bricks, each marked with their own signature. These bricks then had to be transported, likely by human porters, to the building site, where they were sorted and laid in specific patterns and columns, creating a giant, cohesive structure from a mosaic of individual contributions. This implies a level of administrative control and social organization that rivals the great works of the Roman Empire, a sophisticated command economy capable of marshalling labor and resources on an almost industrial scale. The pyramid itself was more than a monument. It was a physical ledger of an entire society's collective effort, a testament to a political and engineering genius that vanished from the region for centuries after the Moche civilization itself faded into dust. A Viking longship rides the crest of a North Atlantic swell, its world reduced to iron-gray water and a featureless sky. The sun has vanished behind a solid ceiling of cloud, and the stars are a distant memory. In this realm of absolute directional ambiguity, a Norse navigator reaches not for a compass, but for a small, translucent crystal. This was the legendary sunstone, a tool spoken of in sagas that allowed these master mariners to find their way across thousands of miles of open ocean. No physical sunstone has ever been found with a runic label, but the strongest candidate is a natural mineral known as Iceland spar, a form of calcite crystal that performs a neat trick with light. It exhibits a property called birefringence, splitting a single beam of light into two separate rays. To use it, the navigator would hold the crystal up to the sky and slowly rotate it. Even on an overcast day, sunlight becomes partially polarized, its waves organized in a specific direction. When the crystal was aligned with this hidden polarization pattern, the two beams of light passing through it would appear equally bright. This alignment pointed unerringly toward the sun's position, even if it was well below the horizon. It was a celestial compass locked inside a piece of rock, a device that used the fundamental physics of light itself as a guide. This was not magic, but applied optical crystallography, a sophisticated understanding that light held hidden information about its source. While formal science would not describe polarization for centuries, Viking navigators were already using it to cross seas that would have been impenetrable to other sailors of their age. Their voyages were not just feats of endurance but of profound observation, a testament to finding direction not in the stars but in the very quality of the light that remained. Centuries before the Romans made it famous, the principle of central heating was already warming Minoan palaces on Crete. Deep within the labyrinthine complexes of Knossos, engineers designed a system that transformed fire into ambient comfort. They constructed floors raised on a grid of short, sturdy pillars, creating a hidden plenum, an empty space beneath the living quarters. A constantly burning furnace, often situated just outside the main walls, would channel its hot air and smoke through this subterranean cavity. The heat would then rise steadily, warming the stone and clay tiles above until the entire floor became a giant, radiant panel. This was the hypocaust, a word meaning fire beneath. The genius of this design was its understanding of thermodynamics, of how heat seeks to rise and how a massive thermal mass can store and gently release warmth. In the winter, a Minoan elite could walk barefoot on a warm floor, the chill of the stone banished by an invisible current of air. The Romans later adopted and refined this technology on a colossal scale, channeling hypocaust heat through hollow walls in their vast public bathhouses, creating sprawling social centers that were cozy even in the depths of winter. This was not a primitive attempt. It was a complete and effective climate control system, a standard of comfort that would vanish from Europe for over 1,000 years after the fall of Rome. Medieval castles were drafty, smoky places in comparison, their inhabitants huddling close to inadequate fireplaces. The widespread comfort of central heating would not return until the 19th century, making the Minoan hypocaust a 2,000-year leap in architectural livability, all achieved by simply mastering the silent journey of heat through empty space. A lost nose could mean a lifetime of social exile in ancient India, a punishment for crime or a casualty of war. Yet a text from 600 years before the Common Era reveals this was not always a permanent sentence. The Sushruta Samhita, a monumental Sanskrit encyclopedia of medicine, details a procedure to craft a new one. The text instructs the surgeon to take a leaf, cut it to the exact size and shape of the patient's lost nose, and use it as a pattern. This template was then placed on the patient's cheek, and a flap of living skin was carefully sliced but not fully removed, leaving it connected by a stalk of flesh to ensure a continuous blood supply. This living graft was then twisted and sutured into place on the face, reconstructing the nasal structure. The patient's arms were often tied down to prevent them from disturbing the delicate new organ as it healed. This was more than simple repair, it was the birth of plastic surgery. Sushrutar's text describes this and other reconstructions for ears and lips with a chilling, methodical precision. His work displays a profound grasp of human anatomy, gained not from books but from the hands-on practice of dissing cadavers, often ones that had been submerged in water to soften the tissues for days. He understood the critical importance of cleanliness, instructing surgeons to fumigate the operating room with vapors of mustard and other herbs, a primitive but effective form of antisepsis that aimed to ward off the invisible agents of infection. He systematized over 120 different surgical instruments and classified hundreds of diseases. This comprehensive system of medicine, with its focus on practical, repeatable surgical solutions, would not find its parallel in Europe until the 18th and 19th centuries, a gap of over 2,000 years. The Sushruta Samhita stands as a quiet, monumental pillar of medical history, a testament to a time when the art of rebuilding the human body was already a refined and sophisticated science. From a surgeon's intimate knowledge of the human cheek, we now shift to a canvas of impossible scale. The Nazca Desert of southern Peru holds a gallery of giants. Etched into the sun-baked pampa are hundreds of geometric lines and sprawling figures, a hummingbird with wings outstretched, a spider with legs elegantly curved, a monkey with a spiraling tail. These are not small sketches, they are colossal geoglyphs, some stretching over 1,200 feet in length, so vast that they can only be comprehended in their entirety from the air. Their creators, the Nazca people, who crafted them between 500 years before the Common Era and 500 years after, never had that vantage point. They walked beside their creation, unable to see the whole picture taking shape at their feet. This is the central mystery. How did they achieve such precision without the ability to look down? The answer lies not in alien architects, but in a masterful application of basic, yet sophisticated, surveying techniques. They likely used a series of stakes and ropes to plot out the figures from a central point, scaling up a small model into a monumental design. By carefully sighting along these lines and using the unchanging horizon or known mountain peaks as references, they could extend perfectly straight paths for miles across the desert floor. The figures themselves, with their elegant, proportional curves, reveal a profound, practical grasp of geometry. The true purpose of these immense drawings remains one of archaeology's great debates. Were they a giant astronomical calendar, their lines pointing to celestial events on the horizon? Or were they sacred pathways, walked during rituals to petition the gods for water in this brutally arid landscape? Perhaps they were meant for the deities themselves, massive signs only visible from the heavens. Whatever their intention, their existence is a testament to a culture capable of extraordinary large-scale planning and communal execution, a society that could translate a complex vision across miles of desert, leaving a message for the sky that would endure for 2 millennia. The cold, hardened ash of Pompeii preserved more than just the final moments of its inhabitants. It saved for us a complete snapshot of Roman medical science. Excavations there and at other sites have unearthed toolkits that feel unnervingly modern. Laid out on a cloth today, you would see bone forceps for extracting arrowheads, finely balanced scalpels with interchangeable steel blades, and complex catheter tubes designed to clear obstructions. One of the most recognizable instruments is the vaginal speculum, a bronze device with a screw mechanism that opens its blades in a design nearly identical to those used in gynecology for centuries. These were not general-purpose tools. Each was a specialized instrument for a specific and often delicate task. Roman medical texts, like those of the physician Galen, describe the procedures these tools enabled in meticulous detail. Surgeons performed cataract surgery by delicately displacing the clouded lens with a needle, a technique that restored sight. They conducted lithotomies to remove bladder stones through a precise perineal incision, and they even performed trepanation, the drilling of a hole in the skull, likely to relieve pressure from head injuries. This was not mere butchery. It was a field of sophisticated specialization, with tools and techniques developed through systematic anatomical study, often gained from treating gladiatorial wounds. This entire ecosystem of advanced medicine, with its specialized instruments and documented procedures, collapsed with the Roman Empire. The knowledge was scattered, the tools were lost or melted down, and the level of surgical precision and specialization they represent would not be seen again in Europe until the Renaissance, a gap of over 1,000 years. The quiet efficiency of these bronze and steel implements speaks of a world that had already mapped a path to modern surgery, only to have that path buried by the very ash that preserved the evidence. While individual inventions capture our attention, the most powerful innovation of all may be an environment that systematically produces them. In 9th century Baghdad, the Abbasid caliphs built such an engine of progress, known as the Beit al-Hikmah, or the House of Wisdom. This was far more than a library. It was a vibrant, state-sponsored academy that became the intellectual center of the world. Its core mission was one of deliberate and radical inclusion. Scholars from diverse backgrounds, Muslim, Christian, Jewish, and Zoroastrian, worked side by side, united not by faith but by a shared hunger for knowledge. Their first great task was a monumental translation project. They scoured the known world for manuscripts, seeking out the works of Greek philosophers like Plato and Aristotle, the medical texts of Galen, the mathematical genius of Indian scholars, and the astronomical tables of the Persians. These were not simply copied, they were translated into Arabic, analyzed, debated, and crucially, corrected and expanded. This process did not just preserve ancient knowledge from being lost to the Dark Ages settling over Europe, it actively refined and advanced it. From this collaborative cauldron emerged entirely new fields of study. The Persian scholar Al-Khwarizmi systematized the solving of equations in his seminal work, Hisab al-Jabr wa al-Muqabala, giving the world the word algebra. The scientist Ibn al-Haytham conducted groundbreaking experiments on light and vision, laying the foundations for modern optics and correctly arguing that we see because light enters our eyes, not because our eyes emit rays. This model of centralized, state-funded research and open cultural exchange was an innovation in itself, a blueprint for the modern research university. The House of Wisdom demonstrates that the greatest invention is not always a gadget, but a system, a space where minds can connect, where past knowledge is not entombed but used as a foundation to build a smarter future. It stands as a timeless lesson in what humanity can achieve when we create the right conditions for genius to flourish. The Antikythera Mechanism was not a solitary miracle. Cicero's own writings describe a bronze sphere constructed by the legendary Archimedes, a device that captured the celestial dance of the sun, moon, and 5 known planets with such accuracy that it showed the very eclipses of the sun and moon as they occurred in the sky. This was not a vague description, it was the account of a sophisticated orrery, a working model of the solar system. Other Greek and Roman authors mention similar planetaria, suggesting that the creation of these cosmic simulators was a recognized, if elite, pursuit among the natural philosophers of the Hellenistic age. The genius of the Antikythera device was therefore not born in isolation. It was the pinnacle of an established tradition of mechanical computation, a school of thought that viewed the universe as a complex, predictable machine that could be mirrored with gears and dials. These artisans and astronomers had moved far beyond simple timekeeping. They were building analog computers, physical representations of mathematical theories that could predict celestial events decades in advance. The profound tragedy is that this entire technological lineage, this tradition of building machines to understand the cosmos, vanished from history. The knowledge of precision gear cutting, the complex astronomical theories required to program such devices, and the very desire to create them were lost in the turmoil that followed the classical world's decline. The mechanical computer was an idea whose time had come, and then, for over a millennium, had gone. This recurring pattern of brilliance and loss forces a humbling realization. Our journey through these 25 marvels reveals that human genius is not a steadily rising line on a chart, but a flickering flame, leaping brightly in one civilization only to be snuffed out by chaos, conquest, or the slow erosion of time. The great library of Alexandria, with its aim to hold all the world's knowledge, was eventually scattered to the winds. The master smiths who forged Damascus steel took their nanoscale secrets to the grave. The architects who understood Roman concrete saw their recipe buried with their empire. These were not mere setbacks, they were catastrophic resets for human capability. Each collapse, each burned library, each faded trade route severed a chain of transmission, casting entire fields of advanced understanding back into the dark. This cyclical rhythm of discovery and amnesia challenges our most basic assumption that progress is inevitable. It suggests instead that our technological ascent is fragile, a climb that can be undone by a single generation's failure to safeguard what it has learned. The true legacy of these ancient inventions is not just their individual cleverness, but the stark warning they collectively carry. They remind us that knowledge is not a possession, but a trust. It requires active preservation, open sharing, and a society stable enough to pass the torch from one hand to the next without letting the flame go out. Our modern world, with its digital archives and global networks, might feel immune to such losses, but the lesson of history is clear. Every advanced society before us thought the same. The quiet, corroded gears of the Antikythera Mechanism ask us a final, haunting question. What masterpieces of our own age might one day lie forgotten, waiting for a future civilization to unearth them, and wonder how we too could have been so brilliantly, so tragically ahead of our time? From the intricate gears of the Antikythera Mechanism to the rust-resistant iron of Delhi, these 25 ancient inventions reveal a history far more technologically sophisticated than we often imagine. They are not merely artifacts, but monuments to human creativity, proving that genius is not confined to any single era. Each one of these marvels, from the self-healing Roman concrete to the Damascus steel forged with nanowires, stands as a powerful rebuke to the idea of a linear march of progress. Our ancestors were not primitive, they were pioneers, solving complex problems with the materials and knowledge they had, achieving feats that would be lost for centuries. As the philosopher Seneca once noted, the time will come when diligent research over long periods will bring to light things which now lie hidden. That time is now. These discoveries invite us to look at the past with fresh eyes, to see the rubble of ancient sites not as ruins, but as the scattered pages of a forgotten instruction manual for a different kind of modernity. More importantly, they challenge us to approach our own future with the same boundless curiosity that drove those ancient minds to reach for what seemed impossible. What hidden knowledge are we on the verge of uncovering next? If you found this journey through ancient innovation as fascinating as I did, please share your thoughts in the comments and subscribe for more explorations into history's greatest mysteries.